A garbage truck is a mobile industrial platform designed to solve several problems simultaneously. It must navigate narrow streets, stop hundreds of times a day, carry irregular materials, withstand corrosive liquids, compact waste without breaking down, protect the operators, and unload tons of material in just a few minutes. The vehicle's foundation is the chassis. It's the structure that supports the entire assembly. The engine, transmission, axles, suspension, cab, and collection body are mounted on it. In many cases, the chassis comes from heavy-duty truck manufacturers, while the compactor body is made by companies specializing in sanitation equipment. This combination allows the same type of truck to be adapted to different collection methods. The engine must withstand a very different type of work than that of a highway truck. A semi-trailer traveling between cities maintains relatively constant speeds for long periods. A garbage truck, on the other hand, travels only a few meters, stops, accelerates again, activates hydraulic systems, brakes once more, and repeats the cycle for hours. That pattern puts a lot of stress on the engine, transmission, brakes, and cooling system. The collection body is the visible heart of the vehicle. It has a loading hopper, a compaction chamber, a storage body, and an ejection system. The hopper is the opening where bags, containers, or loose waste are placed. On rear-loading trucks, this opening is located at the back. On side-loading trucks, it's on the side. On front-loading trucks, it's fed from above by large arms that lift industrial containers. The storage body looks like a closed box, but inside, it's designed to withstand enormous pressures. It can't be a simple, rectangular metal box. Waste presses against the walls from irregular angles, liquids accumulate at the bottom, hard objects hit the interior, and compaction generates repeated stresses. That's why high-strength steels, structural reinforcements, robust welds, and surfaces that reduce pressure points are used. Hydraulics is the system that powers almost everything. A hydraulic pump takes mechanical energy from the engine, usually through a power takeoff, and pressurizes oil. The oil travels through hoses and valves to cylinders that push plates, raise arms, open gates, and activate discharge mechanisms. The physical principle is simple, but its application is powerful. A pressurized fluid transmits force in a controlled manner, and that force can be multiplied to move parts weighing hundreds of kilograms. The compaction system is one of the most important parts. In a rear-loading truck, waste falls into the rear hopper. There, a sweeper plate or sweeper blade pulls the material inward. Then a compactor plate pushes it against the already stored waste. With each cycle, the garbage is compressed a little more. Bags tear, air escapes, hollow objects are crushed, and the overall volume decreases. Compaction isn't about completely destroying the waste, but rather increasing the amount that fits in the truck. A city doesn't need to transport air. Much of household waste takes up volume because it's full of empty spaces. Inflated bags, unfolded boxes, plastic containers, plant debris, and loose items create a very bulky mass. By compacting it, the truck can collect from many more households before returning to unload. The compaction rate varies depending on the type of waste. Cardboard and lightweight plastics are reduced significantly. Food scraps and wet materials are compressed less because they are already dense. Rigid objects, such as thick wood or metal, can resist crushing and cause blockages if too many enter. That's why some systems separate bulky waste and collect it with special vehicles. Another, less visible part is the leachate collection system. When garbage is compressed, it releases liquids. These can come from food scraps, improperly sealed bottles, torn bags, accumulated rainwater, or decomposing organic matter. These liquids must not flow freely onto the street. The truck has channels and compartments that partially contain them until unloading. Even so, when maintenance is poor or the load exceeds certain limits, dark, foul-smelling trails can appear behind some vehicles. The cab is also part of the system's engineering. It must offer good visibility, accessible controls, communication with the operators, and resistance to heavy use. Many modern trucks have cameras, proximity sensors, weighing systems, route displays, external controls, and emergency stop buttons. The vehicle operates near pedestrians, parked cars, cyclists, poles, wires, trees, and poorly placed containers. Safety depends as much on the machine as on human coordination. Collection begins long before the truck arrives at the block. At operations centers, routes, schedules, crews, waste types, and unloading zones are defined. A truck doesn't travel randomly through the city. Its route is designed to cover the greatest number of points with the least possible expenditure of time, fuel, and wear and tear. Routes are usually divided into sectors. Each sector has a collection frequency that depends on population density, the type of economic activity, waste generation, and sanitary conditions. A residential neighborhood may require a different frequency than a commercial or restaurant area. A market produces large quantities of organic waste. An office area generates more paper, packaging, and everyday consumer waste. An industrial zone may have special regulations. When the truck enters a street, the operation becomes almost choreographed. In traditional rear-loading systems, one or more operators get out or ride on external platforms authorized according to local regulations. They take bags, small containers, or receptacles and empty them into the hopper. The driver moves slowly, stops at each point, and maintains constant communication with the crew. Rear-loading garbage trucks offer flexibility. They allow for the collection of loose bags, irregular waste, and containers of varying sizes. This makes them common in neighborhoods with narrow streets or less standardized collection systems. Their disadvantage is their greater reliance on human physical effort. Operators lift heavy loads, are exposed to traffic, sharp objects, contaminated liquids, and repetitive movements. For this reason, many cities have moved towards standardized containers and mechanized systems. Side-loading trucks use a robotic arm located on the side of the vehicle. The driver aligns the truck with the container, activates the system, the arm hugs the container, lifts it, inverts it into the hopper, and lowers it back onto the ground. In some models, a single person can operate the entire process from the cab. This reduces workplace exposure and speeds up collection, but it requires suitable streets, compatible containers, and precise placement. If a parked car blocks the container, the system loses efficiency. Front-loading trucks work with large containers, common in commercial, residential, light industrial, and high waste-generating areas. They have two front arms that insert into side pockets of the container. They then lift it above the cab and empty it into the top of the truck. The movement seems simple, but it demands great stability. Lifting a heavy container above the vehicle shifts the center of gravity. That's why chassis design, weight distribution, and load limits are critical. The moment the waste enters, the truck is the beginning of a physical transformation. The hopper receives a wide variety of materials. There are soft bags, boxes, organic waste, bottles, fabrics, dust, branches, improperly disposed of small appliances, and items that should never have been there, such as batteries, aerosols, chemicals, loose glass, and medical waste. The truck is designed to handle a variety of materials, but not to neutralize all hazards. Hazardous objects are one of the biggest hidden problems. A lithium battery can ignite if punctured during compaction. An aerosol can explode under pressure. Broken glass can cut an operator before entering the hopper. A chemical can react with other waste. On the surface, the garbage appears as a uniform mass. Inside the truck, however, each object retains its risks. When the hopper reaches a certain level, the compaction cycle is activated. In modern trucks, the process can be automatic, semi-automatic, or manually controlled. The plate collects the waste and pushes it into the main chamber. The metallic clang and the crunch of crushed bags are signs that the system is reducing volume. With each cycle, the resistance increases. At first, the material enters easily. Later, as the body fills, the compactor must push against an increasingly dense mass. The internal pressure is not perfectly distributed. The garbage behaves like a chaotic material. It is not liquid, it is not a uniform solid, it is not dry sand. It's a mixture of objects that deform, break, jam, and settle. This irregularity explains why some trucks seem to fill up prematurely or why certain loads make compaction difficult. A large amount of unfolded cardboard can take up too much space. A load of wet waste can become very heavy before filling the available volume. Weight is just as important as volume. A garbage truck may have free space and still not need to continue loading if it reaches the legal weight limit. Exceeding that limit damages axles, brakes, tires, and pavement. It also increases braking distance and the risk of rollover. That's why many systems include scales on the vehicle or controls at transfer stations. The truck isn't only filled by space, but also by mass. Urban garbage collection has a constant enemy: time. Every stop adds seconds. Every blocked container adds minutes. Every congested street reduces efficiency. Every reversing maneuver increases risk. That's why routes tend to be organized according to traffic flow, off-peak hours, and the location of critical points. In densely populated areas, the difference between a well-designed route and an improvised one can mean thousands of liters of fuel per year. The operation also depends on the city's behavior. When waste is put out outside of designated collection times, containers overflow. When hazardous materials are mixed with regular garbage, the risk to workers and facilities increases. When cars block containers, the truck loses time or leaves waste uncollected. When it rains, the garbage weighs more and liquids multiply. The machine may be powerful, but it operates within an unpredictable urban ecosystem. Compaction is the key to the garbage truck's success. Without it, modern garbage collection would be much slower, more expensive, and more polluting. A truck without a compactor would have to unload much more frequently, travel farther, and use more vehicles to collect the same amount of waste. Compaction transforms a volume problem into a density problem. The principle is based on reducing empty space. Many garbage bags contain air between items. A box occupies the same space, whether empty or full, until it is crushed. A plastic bottle maintains its shape due to rigidity, not its contents. A bag of mixed containers looks large, but much of its volume is hollow. When the compactor plate presses down, those empty spaces disappear. The hydraulic system allows force to be applied in a controlled manner. The pump sends pressurized oil to cylinders. The cylinders push articulated arms or plates. Valves regulate direction, speed, and sequence. If the pressure exceeds a limit, a relief valve protects the system. Without this protection, a blockage could rupture hoses, deform parts, or damage the structure. In rear-loading trucks, the mechanism typically has two main movements. First, a sweeping plate collects the waste from the hopper. Then, a compaction plate pushes it into the body. In some designs, both plates work in a sequence similar to a mechanical jaw. The material is drawn in, compressed, and moved. The cycle is repeated hundreds of times per day. The sound of compaction reveals a lot about what's happening inside. Dry crunching might come from boxes or small furniture. High-pitched clicks could indicate rigid plastics. Metallic clangs might come from unsuitable items. Liquids create splashes and drips. Even though the operation seems uniform, each load produces a different response. Pressure doesn't just crush, it also mixes. A bag that goes in sealed might tear, releasing its contents and mixing them with others. Organic matter sticks to paper and cardboard. Liquids soak into dry materials. Glass fragments scatter. That's why, when ordinary garbage goes into a compactor truck, subsequent sorting becomes much more difficult. Compaction improves transport, but it worsens material recovery if there hasn't been prior separation. That's one of the paradoxes of the system. To move waste efficiently, the truck needs to compact it. To recycle more effectively, the materials should be kept clean and separated. That's why many cities use different trucks for dry waste, organic waste, yard waste, bulky items, and recyclables. A recycling truck may compact less or with less force to avoid damaging valuable materials. A broken glass bottle loses value and contaminates other waste streams. Clean cardboard mixed with food scraps is no longer recyclable in many processes. Compaction also generates heat through friction and deformation, although it doesn't usually reach extreme temperatures. The real thermal risk arises when reactive materials enter the system. Lithium batteries, hot ashes, poorly extinguished embers, aerosols, or chemicals can start fires inside the load. A fire in a garbage truck is especially dangerous because the material is compressed, mixed, and full of small combustibles. It can burn slowly inside before becoming visible. When smoke or fire is detected, many operations recommend unloading the contents in a safe area, away from buildings and vehicles. Extinguishing a fire inside the compactor can be difficult. Water doesn't always penetrate to the source, and compaction limits access. In addition, some waste can react with water or release irritating gases. Ordinary garbage, under certain conditions, becomes a chemically unpredictable material. Compaction has its limits. If an object that is too large or rigid enters the system, it can clog the hopper. If the material is extremely heavy, it can overload the system. If there is too much wet waste, the load reaches the weight limit before filling the volume. If long branches or elongated pieces predominate, they can get stuck in the compactors. That's why there are specific trucks for green waste, rubble, or bulky items. The final load density depends on the truck's design and the type of waste. An efficient compactor can transport several tons in a single trip. This capacity reduces the number of trips to the dump site. Fewer trips mean less fuel, fewer emissions, less congestion, and fewer operating hours. In a large city, this difference translates into tens or hundreds of trucks every day. The compaction system operates under harsh conditions. It is subjected to impacts, moisture, corrosion, dust, grease, organic debris, and abrasive objects. The hydraulic hoses are under constant pressure. Seals can wear out, plates can warp, hinges and joints require lubrication. A hydraulic failure can take the truck out of service, and a truck out of service can disrupt an entire route. In many large cities, the garbage truck doesn't travel all the way to the final destination. It would be inefficient. Landfills or main processing plants are usually far from the city center. If each small truck had to travel that distance several times a day, hours of work would be lost and too much fuel would be consumed. That's why transfer stations exist. A transfer station acts as an intermediate point. The collection truck enters, is weighed, and unloads its contents into a platform, pit, or hopper. Then, other equipment loads that waste into larger vehicles, such as semi-trailers, compacted containers, or rail cars. The logic is similar to that of passenger or freight transport. Small vehicles collect in densely populated areas. Large vehicles handle the longer routes. Weighing is a fundamental part. Upon entering and leaving the station, the truck passes over scales. The difference between the two weights indicates how many tons it unloaded. This data is used to monitor routes, pay contracts, calculate fees, detect anomalies, and plan capacity. Garbage, which on the street seems like just a visual problem, is transformed into data. Tons per neighborhood, per day, per season, per route type. Unloading the truck is another moment of immense mechanical force. In many models, the rear opens using hydraulic cylinders. Then, an internal ejector plate pushes the entire compacted mass outward. This plate travels the length of the truck from front to back, displacing the waste like a giant piston. The load falls as a single unit, breaks apart, and releases accumulated odors, vapors, and liquids. The unloading reveals the true nature of the contents. What were once separate bags on the street have become a mixed mass. Fragments of plastic, cardboard, organic waste, textiles, packaging, and misshapen objects are all distinguishable. The compaction creates layers, like an artificial geology of urban life. Each section may contain waste from different blocks, times of day, and activities. At a sorting plant, machines and workers try to recover useful materials. Conveyor belts, magnetic separators, screens, air currents, optical sensors, and robotic arms separate metals, plastics, cardboard, and other materials. But the more mixed and dirty the garbage arrives, the more difficult and expensive it is to recover anything. That's why source separation has such a huge impact. Clean waste is a resource. Contaminated waste can become refuse. If the waste is separated into separate organic materials, it can go to composting or anaerobic digestion. In composting, microorganisms transform food scraps, yard waste, and biodegradable materials into a stable product resembling fertile soil. In anaerobic digestion, organic matter decomposes without oxygen, producing biogas, a methane-rich mixture that can be used to generate energy. In both cases, the truck collecting organic waste must avoid mixing it with plastics, glass, or chemicals. If the city uses incineration with energy recovery, the waste is burned in controlled furnaces. The heat produces steam, which drives turbines to generate electricity or district heating. This system significantly reduces the final volume but requires strict emissions controls, gas filtration, and ash management. It's not simply burning trash, It's a complex industrial operation involving controlled temperatures, filters, chemical reactors, and constant monitoring. When the destination is a landfill, the waste is deposited in cells designed to isolate it from the environment. A modern landfill shouldn't be a simple dump. It has impermeable layers, leachate drainage, gas capture, daily cover, and environmental monitoring. Even so, it's still the last link in a chain that attempts to reduce harm. Buried waste doesn't disappear. It slowly transforms, releases gases, produces liquids, and occupies space for decades. The garbage truck, therefore, is not the end of anything. It's the first visible link in a chain. Its unloading initiates another stage of handling, sorting, treatment, or final disposal. Every decision made before collection affects what happens next. A properly sorted bottle can be recycled. The same bottle mixed with organic waste can end up buried. Hazardous waste discarded in a regular bag can damage a machine, injure a worker, or cause a fire. After unloading, the truck can return to its route if there's still time available. In some cases, it goes for a quick cleaning or inspection. In others, it returns to the yard at the end of the shift. Efficiency is measured by tons collected, kilometers traveled, fuel used, hours worked, incidents reported, and route adherence. A collection system isn't evaluated solely on whether the street is clean, but also on the cost of achieving that cleanliness and what happens to the waste afterward. The city sees the truck drive away and assumes the problem is over. In reality, the garbage has barely changed location. It has gone from a sidewalk to a machine, from a machine to a station, from a station to a plant or landfill. The entire journey can take hours, days, or years, depending on the material's destination. What disappears from a house's doorstep enters a silent infrastructure that operates on a metropolitan scale. There are several types of garbage trucks because not all waste or streets present the same problems. Collecting household bags in a narrow neighborhood doesn't require the same machine as collecting commercial containers, recyclables, yard waste, construction debris, or bulky materials. The rear-loading truck is one of the most common. Its main advantage is its versatility. It can handle bags, small containers, and bins compatible with rear lifts. It works well in areas where the container infrastructure isn't fully standardized. It also allows for direct intervention by operators when waste is overflowing. Its disadvantages are greater human exposure and, in some cases, a slower operating speed. The automated side-loading truck represents a step toward mechanization. Its arm picks up standardized containers and empties them without the driver leaving the cab. This improves safety and allows for faster routes when conditions are ideal. But the system needs to be organized. The containers must be properly oriented, unobstructed, and within the arm's reach. The city must adapt to the machine as much as the machine adapts to the city. Front-loading trucks are widely used for large commercial or community containers. Their front arms lift the container and unload it from above. They offer high capacity and efficiency in high-volume locations. However, they require maneuvering space and sufficient headroom. Low-hanging wires, branches, awnings, or roofs can obstruct operation. There are also smaller or satellite trucks. These are used in narrow streets, historic centers, pedestrian zones, or areas where a large compactor cannot enter. These vehicles collect waste and then transfer it to larger units. Their capacity is limited, but they solve the access problem. Trucks for recyclable waste can have special designs. Some have separate compartments for different fractions. Others compact less intensely to preserve materials. There are also vehicles dedicated to paper and cardboard, glass, containers, or mixed dry waste. The key is to prevent recyclable materials from becoming contaminated. Trucks for organic waste usually have more airtight containers, washing systems, and better liquid control. Organic matter is heavy, moist, and odorous. It decomposes quickly, attracts insects, and produces leachate. A truck designed for organic waste must better contain this load and be cleaned frequently. Bulky waste, such as furniture, mattresses, or appliances, requires a different approach. A standard compactor can be damaged if it receives objects that are too large or rigid. For these materials, open bed trucks, cranes, flatbeds, or specific loading systems are used. Some bulky items are dismantled or crushed at separate facilities. Construction debris is also a special case. It's dense, abrasive, and can quickly exceed weight limits. A city compactor truck isn't designed to carry large quantities of brick, cement, or ceramic. Dump trucks, heavy-duty trucks, or construction containers are used for that purpose. Mixing construction debris with household waste reduces efficiency and can damage equipment. Choosing the right truck depends on a complex equation: urban density, type of waste, street width, climate, budget, labor regulations, container infrastructure, distance to unloading facilities, and population habits. There is no single perfect truck for everything. Each design solves a problem and creates certain limitations. In modern cities, the trend is toward more efficient, less polluting, and better connected vehicles. Some trucks run on natural gas, electricity, or hybrid systems. Electrification makes sense because urban waste collection involves frequent stops, low speeds, and predictable routes. An electric truck can recover energy by braking and reduce noise during night shifts. The challenge lies in battery weight, range, initial cost, and charging infrastructure. Intelligent systems are also emerging. Sensors that indicate the weight of the load, cameras that record blocked containers, GPS that confirms routes, software that adjusts routes based on actual waste generation, and containers with fill sensors that alert when they need to be emptied. Collection is no longer solely dependent on fixed schedules and is beginning to move toward data-driven logistics. Even so, technology doesn't eliminate the physical nature of the problem. Garbage remains heavy, wet, irregular, and socially unavoidable. Every technological advance attempts to reduce the cost of moving what the city produces without pause. The garbage truck operates in one of the city's most aggressive environments, not only due to the mechanical conditions, but also because of the human exposure. Collection workers face traffic, weather, weight, odors, sharp objects, slippery surfaces, animals, noise, repetitive movements, and improperly disposed waste. One of the most common risks is cuts and punctures. Broken glass, open cans, needles, sharp metals, and ceramic fragments can pierce bags. Even with gloves and protective equipment, an opaque bag always carries uncertainty. The operator cannot see what they are lifting. This invisibility makes each bag a small gamble. There are also biological risks. Rotting food scraps, diapers, improperly managed sanitary waste, dead animals, or contaminated materials can release bacteria, fungi, and foul odors. Contact doesn't always cause illness, but it increases the need for hygiene protocols, vaccinations, hand washing, work clothes, and proper separation of hazardous waste. Traffic is another major hazard. The truck stops in places where other vehicles don't always expect obstacles. The operation can take place at night, in the rain, or on poorly lit streets. Operators climb up and down, walk close to the roadway, and move around a machine with blind spots. Cameras and alarms help, but they don't replace vigilance. Reversing is especially dangerous. A heavy truck has limited visibility and needs space. Many operating regulations attempt to reduce reversing maneuvers or require outside assistance. Proximity sensors and rear-view cameras have improved safety, but well-designed routes remain a key tool for avoiding risky situations. Truck maintenance is a battle against wear and tear. Brakes suffer from constant stops. The transmission operates in low-speed cycles. Tires bear heavy loads and are subjected to contact with curbs, potholes, and debris. The suspension endures frequent impacts. The hydraulic system operates under pressure throughout the journey. The body faces corrosion from within. Cleanliness is more than just an aesthetic issue. Sticky residue can accelerate corrosion, generate lingering odors, attract insects, and hinder inspections. That's why trucks are washed with pressurized water and appropriate products. Critical areas include hoppers, joints, leachate tanks, compaction plates, and gates. A small buildup can become a mechanical or sanitary problem. Hydraulic leaks are serious failures. Hydraulic oil allows the compactor to move, but if a hose breaks, the system loses power and can contaminate the soil. Furthermore, high-pressure oil can be dangerous for anyone nearby. That's why hoses, connections, seals, and cylinders are inspected. Corrosion is a silent enemy. Organic waste produces acids. Retained liquids attack the metal. In cold climates, the salt used on the streets can accelerate deterioration. A corroded body loses strength and can leak liquids. That's why the interior design, drainage, and protective coatings are crucial. The everyday mystery of the garbage truck lies in its resilience. Few urban machines are treated so harshly, yet they must operate with near-perfect regularity. If an excavator stops, a construction project is delayed. If a delivery truck breaks down, a delivery is postponed. If a garbage fleet stops, the city feels it within hours. Waste doesn't wait. Fleet management tries to prevent that scenario. Operators schedule preventative maintenance, rotate units, conduct daily inspections, and make quick repairs. A truck can have a lifespan of years, but that lifespan depends on the intensity of use, the quality of maintenance, and the type of waste collected. Two identical vehicles can age very differently if they work on different routes. The garbage collection job combines routine and vigilance. Every day, similar movements are repeated, but a dangerous object can always appear. A broken container, a blocked street, an animal in a bag, a battery that starts smoking, or a load that gets stuck. The routine of the service masks constant vigilance. A garbage truck also reveals how a city lives. The composition of the garbage changes depending on the neighborhood, the season, the economic level, consumption habits, holidays, the weather, and crises. Each load contains a kind of material footprint of human activity. After celebrations, packaging, food scraps, and bottles increase. During moves, furniture, cardboard, and broken items appear. During pruning season, green waste grows. In commercial areas, packaging predominates. In restaurant districts, organic waste abounds. In residential neighborhoods, the mix can be more varied. Garbage is a wordless record. Cities use this data to plan. If an area generates too much waste, it may need more containers or more frequent collection. If a route always returns with a low load, it can be reorganized. If a recycling plant receives too much contamination, education, enforcement, or system changes may be required. The truck becomes a mobile source of information. The daily weight of waste also reflects economic changes. When consumption increases, waste usually increases. When there's a recession, the generation of certain materials may decrease. During lockdowns or changes in employment, waste generation patterns shift. Less waste in offices and more in homes. More packaging for home deliveries. More cardboard from online purchases. Waste reflects social transformations before many statistics can even begin to categorize them. There is also a profound environmental dimension. Every bag that goes into the truck represents extracted resources, energy used, previous transportation, and industrial design decisions. A discarded container doesn't begin its story in the trash. Before that, it was oil, minerals, trees, water, electricity, factories, trucks, stores, and consumption. The garbage truck collects the last visible chapter of much longer production chains. That's why modern waste management tries to move up the waste hierarchy. First reduce, then reuse, then recycle, compost or recover energy, and finally landfill only what is unavoidable. The truck participates in that hierarchy, but it can't solve it alone. If the city generates too much mixed waste, the machine only moves the problem around. If the separation is good and the plants are functioning, the truck becomes part of a circular economy. There is a constant tension between convenience and responsibility. Putting a bag out on the street is easy. Designing a system that transforms millions of bags into recoverable materials is difficult. It requires infrastructure, regulations, education, technology, and markets for recycled materials. The truck is the visible face of that system, but not its only component. Poorly managed waste reveals urban failures. Overflowing containers, bags torn open by animals, liquids in the street, irregular collection, or illegal dump sites indicate that the system is not functioning properly. The problem could be the frequency of collection, oversight, budget, civic responsibility, or treatment capacity. Garbage always makes visible what the administration tries to hide. Conversely, efficient garbage collection creates an illusion of disappearance. The street is clean, and the problem seems solved. This illusion is necessary for daily life, but also dangerous. If something disappears from sight too quickly, it can cease to be thought about. The garbage truck operates precisely on this border between the visible and the denied. The vehicle's engineering responds to a practical need. The modern city produces more waste than it can handle. It needs machines to remove it before it accumulates. But every time the compactor closes, a larger question is also closed. What materials were truly necessary, which could have been avoided, which could be returned to the